sugar boost will last. Let me put the timer so that I know how much time I have. Okay, okay, let's just do a lightning review of what we've seen this last hour and a half. We've studied the expectation value of the quantum stress energy tensor for different choices of the vacuum states on top of an external Schwarzschild black hole. And actually, this also gave us some information about the collapsing case. Right? And we've seen that the physics depends on the vacuum you choose, unsurprisingly. And we've seen different features. We've seen that we have one vacuum, which is the Boulevard vacuum, which is the vacuum that you expect to describe static configurations, because it's something which is vacuum, so it's empty, the vacuum which is empty on square minus, and also you have nothing on square plus, and everything is time independent. So it's the vacuum that you expect to describe static situation, but it doesn't really work on black hole because it's divergent at the horizons. The only state which is fine for black holes is a state which has thermal radiation both on square minus and on square plus, and this means that you don't really have a particle creation. You just have a thermal bath, and the black hole living in this thermal bath. Is this physical? Well, the physical object that we know are objects that are formed at some point. So that's why it's not particularly worrisome the fact that you have infinite bath of energy everywhere. But it's interesting to study this vacuum. But also we had described another vacuum, which is the Unruh vacuum, which was not regular everywhere, because it was divergent at the past white hole horizon, but that approximates a late time the in vacuum, the vacuum that you obtain considering gravitational collapse. So that Unruh vacuum is also something which is quite useful because it gives you some qualitatively good physics, and the fact is divergence in some region of space-time is not particularly worrisome because those are regions that are not necessarily physical. Okay, brava. Yeah. If you apply boost like a Lorentz group, nothing changes because everything is Lorentz invariant. But locally, yeah. Yeah, that's the full point. That with a generic differential transformation, you change the vacuum, you go from one vacuum to the other. So this is exactly the point. Different observers see different things. Exactly. Yeah, we cannot measure, but this is exactly, yeah. But I mean, there is no correct description. It's different server will say different things. It's like the Ur effect, right? If you have an inertial observer, you can define a vacuum. If you have a accelerated observer, you will define a different vacuum, and that's it. The vacuum is different, and it's depend on how you prepare your system, right? It depends on how you do the measurement, but there's no wrong and correct picture. Okay, yeah, that's different. Cosmology is different. Yeah. Of course, I mean, choosing the vacuum state has implications. But what I mean is that it's not like one choice is correct and one is wrong. It's wrong. It's how you choose your initial. It's the same as choosing initial conditions. Yeah, I mean, using the state is like how I define the vacuum state in some way, but nothing is telling me that I am in the vacuum state. I can be in an excited state, right? So the definition of the vacuum state is something, but then whether or not you are in this vacuum state that you define this way is something that is just depends on the initial condition. So it's observation. Yeah, exactly. It's different physical situation. Um, Now, before going forward, I asked a question. I will remind you. Um, I was discussing. I don't remember the name. It's Marco. Yes, I knew the name. I was discussing with Marco before that asked me a question about back reaction, and yeah, maybe we can say something which is interesting. And all we've done now was to compute this well to compute to write down because this is something that someone says computed, which is the expectation value of the stress energy tensor. But I say that something you can do as a first order is to plug it into the Einstein field equations, where you may or may not have some classical matter plus, well, G, G, E, expectation value. And we can also ignore the interaction between the quantum fields and the classical matter. Right? And what we could do is to study, for instance, the gravitational collapse in this um, with this setup, and see what are the effects of this gravitational collapse. This is something that we can do in 2 dimension, and hope that this teaches us something in 4 dimension. The reason why you can do in 2 dimension is exactly what I mentioned before, that you have the expression, the analytical expression of the vacuum state in terms of the metric, right? Whatever is your 2 dimensional matrix, you can write down the expression of, sorry, the vacuum state, the stress energy tensor. So you can write down an equation here and solve itself consistently. And now I want to ask you a few questions, whether or not to see if you can have some intuition of what you can expect to happen as a result of this back reaction, right? And of course, you will need to do the computation, but let's see if you can, um, if you have some intuition based on what we said before. So let's imagine that we have. So let's answer this question. Will you have? Maybe we are interested on the question of whether or not we can avoid the formation of an horizon due to these effects. Because we know that classically we will always form an horizon if we satisfy a certain disequality. You cannot stop it, right? This is due to the energy condition that we know that they are violated because what we were discussing with Rava. But let's try to understand whether or not we can have some very strong effect and avoid the formation of such horizon. And so let's start from the case in which we have some matter collapsing, and it's basically free falling at the very close to the Wolbe horizon. So would you expect quantum effects to be very large or to be negligible? This is something that we can try to imagine and see if we have an intuition. So if I have something which is free falling, the vacuum should be very similar to the in state. So at the horizon formation, very similar to the Uru state that we described before. So what you would think will be the effect of this? Plugging this into the Einstein equation. Would you expect to be something large, be small, and also why? So we can expect this to be in the Uru state, right? Very close to the Uru state at least. Yeah, the question is if I plug these quantum effects into the equation and I try to solve them consistently, right? Whether or not I will see a very large deviation once I'm approaching the horizon and I'm approaching like at a free falling with the horizon, right? So yeah, it could be like yeah. So I mean, of course, you cannot know the answer without doing a computation, but just thinking the state, the Uru state, is something which is well defined at the horizon, right? So you can expect some modification, right? But they're not necessarily huge, right? So we don't really expect, like, if you do the computation, if you have something which is free falling, this modification you can see they turn out to be quite small, right? And This is something you need to check. But the point is that the Eurostat, I mean, it's something you can imagine happening because we have said before that null observer crossing your horizon in Eurostate don't see anything special, right? So of course there is a non-zero effect because they see something, but we said before they see something small. They don't see something huge. And so we can imagine also the matter collapsing if I do this self-consistently, will not see something huge. But now the question I wanted to ask you is what happens instead if I do the collapse very, very slowly, like a series of adiabatic state. I take a star and I draw over the radius very, very slowly. Some other process is slowing down. What do you think will happen? So what do you think will be the state, the quantum state? And what do you think will be the consequences of this? So let's start from the quantum state, right? Like just a random guess. Any of you, like give a kind of random guess of what will be the could be. I mean, it's not something that is not actually obvious, but initially Boulevard State. Why? Hmm. Yeah, yeah. But I said, let's imagine that goes very slowly, a series of adiabatic process. There is something that is slowing down a lot this process. So I'm going very, very slowly. So you would expect to stay in the Boulevard State. Of course, should be checked. It's not. I'm not even 100% sure this will happen. Right? This is something just an intuition. There are works on this direction, but there are also open questions. So we can expect, let's expect that we will stay in the Boulevard State. Uh, then what do you think will happen? Will you form on the horizon or not? If this is true, that we stay in the Euro state, getting closer and closer to something very compact, to R closer and closer to the Schwarzschild limit, very slowly. Mhm. Why? Mhm. No, no, but I mean, imagine that this effect here. I mean, what is this? What is this doing? Once you try to form the horizon, like you get closer and closer, there is a process that slow down, which is not given by this. But imagine that you are very close to the formation and still static. Uh, what is this going to do? We said we are in the Boulevard state. What is the Boulevard state at the horizon? Yeah, it's going to be arbitrarily large. And so it's going to oppose with arbitrarily large the formation of the horizon, right? And this is only true if you are extremely close to the horizon in a static configuration and you let it go. And in fact, there are several works that you start. I said that I was going to talk about regular black holes, and this is something that is related to that. There are several works that try to deal with the singularity, thinking, okay, can I avoid the formation of the singularity just by avoiding the formation of the horizon itself? And it turns out that if you just start and you collapse matter and you free falling, no, you cannot do that. But if there is some other thing, some other process that we don't really know yet, and then once we are very close to the formation of the horizon, then this becomes huge. Then it turns out that there are static solutions that seems to be stable. There are other issues to be addressed about the stability, but there are static solutions supported uniquely by this. And the reason is because the Boolevard state will diverge at the horizon. So if I get very close to having an horizon in the Boolevard state, I will have a huge term that will not let me create the horizon, because otherwise I will get this divergence. Of course, there are subtleties because you will not be exactly at the Boulevard state. You will be close to the Boulevard state, so the effect will be large, not huge, but not infinity. So there are still open questions. But this is just to say that this is not enough to have a non-regular a non-singular black hole, but it is definitely something that can play some role that it could support. At least static solution could be there. Then how to reach that solution? I don't know. You will need something which is fully quantum gravity. But at least you can study this solution in the context of semi-classical gravity, which is something which has a very well-defined equation of motion and has a very well justified uh, justified setup, because this is just the first effect. But the price to pay is that you need to say somehow you get there, and we don't know how to get there. But at least you can study the consequences if you get there, right? This was just to answer the question that Marco asked me during the break, and I thought it was quite interesting, so I wanted to answer it in front of everyone. So yeah, thank you for the question. Yeah, but we didn't really regularize the divergence. We just say that the dynamics chose a different vacuum. But if I am in a static configuration, I cannot create particles, right? So if I assume that there is no particle here, which is a physical realistic configuration, and I go extremely slowly, so it means I'm not going to create a particle because I'm in a diabatic approximation, then I would expect, it's not, it is my expectation, but it's not, I mean, the experiment should confirm whether or not this is true, but you will never be able to do such experiment. My expectation would be that you will not get too far from the vacuum, and so you will form that. Huh? But I mean, it's not only, I said my expectation, it's not only my expectation. There are several works on this, and I think these are reasonable. These are reasonable. But yeah, it's not, of course, it's not proved, but I think it's reasonable. Mhm. Yes. It's basically the first term of the expansion. And of course, and actually, I mean, it's not obvious that this is the leading term. Usually, when you have many fields, then this is the leading term. So we are doing this with one field, but we're expecting there are some situations in which this is the leading term. But yeah, there is a bar there. Okay. No, it's okay. You will check out YouTube later. Okay, the secret. We are now starting the last lecture, and uh, um, and asked you at the end of the second lecture. I asked you a question. We computed that this, I'm tired, so I'm letting you do the work. You can answer. So I don't need to speak too much. We computed in the second lecture. We computed the quantum state on Scray plus. So we started with a pure state on Scray minus, and we checked that on Scray plus, we get a mixed state. And I asked you, but I asked you to actually think about it, not to assume that you know the question, whether or not this is a paradox. And so it would be nice, at least one of you, to give an answer. Of course, I mean, we just want to know your opinion. It's not like, mm, I mean, of course, there is something there because the title of this lecture is the information loss problem. So, of course, there is something. But anyone that wants to give a thought on this, a random person. So the question is, we computed we started from a state which was vacuum here, so a pure state here, and we know that pure state evolved into pure state by unitary evolution. This maybe I should have mentioned, but I guess this is something that you know. So unitary evolution takes pure state and evolve it in new pure state, and then we check that here on Scray plus we have a mixed state. This is a purely thermal state, and the answer is this already a paradox? Like, I mean, maybe I'm asking this question and okay. Hmm. But why only LA times? Like if I go from pure state to a mixed state, is it a problem or not? If I go to a pure state here to a mixed state here, is this a problem or not? And I mean, this is what happens. I start for a pure state here and I get a mixed state here. Is this a problem? Who says yes by raising hands? If you don't raise hand, you say no. Okay, everyone says no. Nice. Okay, I'll just Um, I just asked this question because I think we should take time before giving such a strong conclusion. And the reason is I mentioned several times during the other class, the Screen Plus is not a co-shaper surface. You are missing some modes. You are not taking into account the modes that enter the horizon. So when I computed the expectation value, or at least I told you how to do the computation of the expectation value in the in state, which is the state that we are evolving, for an observer at late times, and omega out and omega out in, I told you that this is an omega out in and omega prime out. So there are no correlations, and this implies that the state, like I'm missing the information. But I also told you that in considering all this Cray plus, I am missing some states. So I never computed the correlation with modes and omega out and at the horizon. I never done that computation, right? So a pure state only needs to be a pure state if I take into consideration all of the manifold, not just Cray plus. So if I take Cauchy surface, like Cauchy surfaces, that for those of you that I mean, it's just causal hypersurfaces, and I have a state here, which is a pure state. I need to evolve it into pure state, right? But Cray plus alone is not a Cauchy surface. So the fact that you're finding a mixed state here, you should expect that because you are losing some of the states. Some of the states are going inside the black hole. But this is completely expected. This is what you should expect. So there is some problem, and this is actually what we are going to discuss today. But at this stage, don't be fooled. At this stage, there is not yet any problem. And in fact, I didn't do this, and this depends on how you define the modus on the horizon, which is not straightforward. But if you do that, you will, like if you do some choices, you will find a correlation between late modes and Scray plus and early modes entering the horizon. And this is definitely not surprising if you look at the causal structure. If you look this region here, arbitrary small region, if you have an observer going epsilon before, they will end up on Scray plus. An observer epsilon after, they will enter the horizon and never end up on Scray plus. So whatever is the correlation of modes here will just be split on very large distances on modes here and modes here. Okay. So of course there are some problems because today we're going to talk about information loss problem, but pay attention. There is no problem at this stage. The model is consistent. And we have also seen that before studying the Uru vacuum, that we have an outgoing flux of energy, but we have also an ingoing flux of negative energy here. And this is the correlated, these states are correlated. So there are correlations here. So let's now define the problem. Will it be a problem if the black hole evaporates completely and we are the only one left with the thermal radiation? Very well. This is exactly the first way I want to define the problem. So the point is this model is self-consistent. So that's why I never call it black hole information paradox, because I don't think it's strictly paradox. On this, I think I am in the vastly minority on the field, but on the fact that we still don't have a problem, I think this is something that everyone agrees. The reason why I don't call it paradox but problem, and most people disagree with me, is that this is all the model is telling you. The semi-classical model, this is what it's telling you. And now we need to go behind this model. And while going behind this model, with some assumption, we will get some contradiction. This means not that the conclusion, I don't think, is going to be paradoxical. I think it's going to be problematic because it means that we need to understand what went wrong in going beyond the model. But the model itself is just not taking care of the back reaction. You have radiation at K+, that radiation is entangled with radiation entering the horizon. No issue, right? So the first way I want to define, I mean, we can define the issue, is complete evaporation, as it was suggested in the chat. Eva. Oh, right. Sure. So it was suggested in the chat. Let me read again the question. Will it be a problem if the black hole evaporates completely and we are left with thermal radiation? So the first formulation of the problem is exactly this. It's telling us that if you assume that pure states evolve into pure states, right? So pure states are defined in this way. They evolve into pure states, psi prime. So it can be different, but it's a pure state. And that we have the complete evaporation. Then let's say then this is a sub point. So complete evaporation, and in this complete evaporation we can trust the computation up to the end. And when I mean complete evaporation, I mean that we also add the fact that the mass is decreasing with evaporation with time, right? So we go we assume that we can trust this computation up to the end, and then we are left with regular spacetime. Then we have a problem. Why? Because then we have a state at the initial. We start with a pure state, and at the end we only have a completely regular spacetime and a mixed state because the radiation is in a mixed state. But I don't think that this formulation of the problem is worrisome for most physicists, because basically, if I look at the Peros diagram, what we have is something which is black hole, which is formed by gravitational collapse. You have this singularity, and then at some point you have complete evaporation, so you're left with the Minkowski spacetime. And then it means that when I say that you go from so this is the event horizon. When you said you go from pure state to mixed state, what I mean is that a state here is pure on this hypersurface sigma. You have a pure state. And according to this, on this hypersurface sigma prime, you will have only radiation, and the radiation will be in a mixed state. And so this is, of course, a contradiction among these two statements. But there are many reasons I don't think this is a problem, and I think most people agree with me. First of all, we cannot really trust this computation up to the end, because this is a semi-classical computation. We cannot trust it up to the end. Secondly, are we sure that we will be left with regular spacetime? What if we are left with something which is a time-like singularity? We don't really know what happens at the end of the operation, so we could be left with a time-like singularity. Third, this is, these points are in the causal future of the singularity. So this point really, we could not trust them uh, with the model that we have. We should this region. We don't really know what's going on because this is a singularity and this is the cusp future. Technically, I would say that as the semi-classical description goes, we have a Cauchy horizon here. If you don't know what is a Cauchy horizon, this is just the boundary of which you can define the initial value problem. And finally, if we forget about all of this, so we assume that this is all goes through, this is regular, we don't care about the Cauchy horizon, nothing, would we really expect a pure state to go into a pure state? I mean, we are missing all this segment of the space-time. We are forming an event horizon. If we truly form an event horizon, we should expect that whatever enters will be disappeared because of the definition. Because an event horizon is a region which is disconnected from the rest of the universe. So why should we expect that that in this picture we should go from pure to pure state? So I think this picture is not really problematic for anyone. I'm going to your formulation now. So if that's your question, then you can answer. Yeah. Yes. Yeah. I will go there. I will go. Huh? Is? Yeah. Well, we will go there. But you see this, you were carrying extra qualification, right? So, yeah. Mhm. I'm going there. Okay. There is no assumption of entropy here. I mean, this is just, in fact, this is why I think no one will really be worried about this formulation of the problem, is because the actual formulation goes in the direction you are going. Then, if it is not what you want to say, you ask the question, okay? Then the second formulation I want to mention is something that uh, it's something that actually was a discussion with Ravan this week, right? Because you mentioned that you expect uh, pure state for uh, outside observer. So one thing that some people require. Yeah. Yeah. Yes. Mhm. Yeah. I mean, this is what I was going to. I mean, you explained it better than I could have because this is your point. So this is exactly what. So Ravan mentioned that I don't only want pure state to evolve into pure states. I want pure states for outside of server to evolve into pure state for outside of server. Now, I come from my expertise is first in classical general relativity, so I am a bit uneasy with this definition because I'm a bit uneasy of associating something special at the horizon, right? But of course, as Ravan was mentioning, this is I mean, it's a valid view, right? This is, but again, we need something extra, right? We need to demand that outside observers that stay outside the the horizon will see pure state. Whereas if I just evolve in the way that I will evolve in semi-classical gravity, this is not what I will get. So of course, this is inconsistent. I mean, of course, this is not realized in this model because the evolution is such that you evolve, from Cauchy hypersurface into Cauchy hypersurfaces, and so part of the information is lost. So the second formulation is like, let's say that we have the evaporating picture. not fully evaporated because we don't need to evolve that. And we have a contradiction from the fact that a pure state on sigma evolves into a pure state of sigma prime, right? So it's just a contradiction between the um, pure state on sigma evolves into a pure state on sigma prime. The contradiction between this and Hawking computation that we just reproduced, the first and the second lecture. Right? Is it clear because why this is in contradiction? Is in contradiction because we have proved that on Scri plus the state is mixed, it's not pure. But this is something extra that we are requiring. Right? This is what I mean. Like every time we define the problem, we need to add something extra. It's not just the model which is in contradicting. The model is not self. I mean, mathematically, the model is self-consistent, right? So yeah. Okay. Let me be more. Let me. You're right. Yeah. Hawking computation, right? And in fact, computation. And in fact, let me cite that, I mean, this is something that Ravan is very active on. Like you have some works to define the evaporation, talking evaporation, such that this happens, right? But again, I want to stress that we are asking something extra, something outside the model. That's why I call it problem. It's not paradox. It's not a contradiction with itself. It's a contradiction with something we put from outside. That's the assumption. That's the assumption that leads to the contradiction. Right? Yes. Yeah, I mean, it cannot be pure if you assume this model. That's what I mean. That's why. So I will say that no one worries about this at all. And I think very few people worry about this. I definitely don't. I mean, huh? Okay, so people in quantum cosmology didn't know, but but they were more worried about this, right? But- okay. So, but yeah, this, I mean, like my personal view is like something that I evolve operators like the way semi-classical gravity does. So I would expect this, and I would expect that there is truly information loss if a formal horizon, because the formal horizon it goes there. So if you're outside, you lose information. But again, some people define the problem in this way. And then I will say that the majority of people are worried about the entropy. Entropy formulation. Okay, what is it about? So this is this is about an inconsistency of this following assumption. First assumption is unitary evolution. So psi goes into psi prime, pure state into pure state. You can see this is always, I mean, this is also the first term. Then the second is that uh, there's like Hawking computation. Hawking computation for large black holes. What I mean by large, for mass much larger than the Planck mass. Uh, well, let me write it bigger because for large black holes, right? And again, these two are not in contradiction. I've discussed before. And then we add that the number of degrees of freedom is the number of maximum degrees of freedom that a black hole can have to entangle with the outside radiation is something which is bounded by the area. So what I mean is that the like the von Neumann entropy or the entanglement entropy, let's just call it entropy, it's smaller or equal than the area divided by some constant, in particular for G. Right? So now this computation, these first two assumptions are, I mean, the first assumption is just unchanged with the one of the complete evaporation. The second assumption is much, much, much weaker because we can definitely expect this computation to work or the large black hole, so in the semi-classical region. But then we need to add another assumption, which is that that you have a bound on the number of degrees of freedom, and this is something which is given by the area of the black hole. Now let's first of all, yeah, because the quality is with thermodynamical entropy, and this is the entanglement entropy. Um, Now we need two things. First, to understand why these three are in contradiction, because it's not as obvious as the other two formulations. And second, to uh, to explain why this is reasonable, because if this is completely reasonable, then okay, who cares, right? So first, why this leads to a problem? And the reason is quite simple of why this leads to a problem. And it is that so in the computation that we had, we assumed that that the mass was constant, and we had this flow of maximally uncorrelated radiation, so thermal radiation. So if I look at the entanglement entropy of that radiation, this is something that I can plot. So the entanglement of the radiation is something that over time, let me write time now, but then of course it's something that we need to say about. It's something which is a monotonic increasing function. Right? On the other hand, we assume we know that within the model, these quanta are correlated with quanta going inside the black hole. So this means, let me call it this S black hole. This means that S black hole should be equal to this quantity here. So actually, let me write as the entanglement of the radiation. So the entanglement entropy of the black hole, of the microstates that are inside the black hole that we don't know how to describe, they should be equal to this quantity here, right? However, what is the area doing? The area is something that we start from a given value, which is I don't know, 2m0, and then it's a monotonically decreasing function of time, because we want to include the fact that black holes do evaporate. So the area is doing something like this. Area over 4G. And so when these two curves meet, then you have something which is impossible because of this assumption here. So this curve, let me actually use different colors. Right, to have a pure state, it means that the entanglement of radiation should be equal to the entanglement of the black hole. But we have this limit So the entanglement of the black hole, the maximum that the entanglement of the black hole can do is something like this. This is the argument. It goes. I mean, it's argument due to page, which is the fact that well, you can actually have exactly equal, but at some point it should start decreasing. And if you check what is this point is when the black hole loses half of its mass because the radiation is maximally uncorrelated. Uh, so, so this argument is this is why this argument leads to contradiction. There is a contradiction among these statements. Uh, and very nice. But then you may ask, okay, but why do we add this requirement here? Right? And there are several reasons to add that requirement there, which are related to this equality. So this entropy here is the entropy is uh, the entanglement entropy is a microscopic definition of the entropy. So it's basically the number of microstates that are entangled with with something outside the black hole, which is definitely smaller than the maximum number of microstates you can have, which is what is completed by the von Neumann entropy. And then any system, any thermodynamical for any system, we have this equality that the von Neumann entropy is smaller than the thermodynamical entropy. This is something that if you've done any course in quantum statistical physics, you will have seen. Just go back and check the definition of the two. I will have more details in the notes. This is something that is always holds true. Right? So the von Neumann entropy is always smaller or equal than the thermodynamical entropy. And so now the question is, why do black holes and then so why this equality? This is because we have several results that tell us that the thermodynamical entropy of black holes is that quantity over there. So the thermodynamical entropy of black holes is equal to A over 4G. And there are several arguments there are several derivations of that quantity. I guess you're familiar with the analogies between the laws of thermodynamics and black hole mechanics. If you're not, it's just that you can have a very nice one-to-one correspondence between the laws of mechanics, of black hole mechanics, and the laws of thermodynamics. And this correspondence is that so the zero law of thermodynamics is the temperature is uniform, and you have that the surface gravity on black hole horizon is also uniform. This is something you can prove in the black hole spacetime. Then the first law is just energy conservation for thermodynamics, and you have exactly the same law in black hole mechanics. And in that law, the role of the entropy is played by the area of the black hole. Okay. And then there is some temperature. In this analogy, there is a temperature which is something which is proportional to the surface gravity of the black hole, which is something which is amazing because the computation is purely classical, and this is a purely mathematical analogy. And then you go and you put quantum fields, and you see that they do actually evaporate with this temperature. And then you have a second. You also have a second law that in thermodynamics is just that the entropy increases with time. And in black hole mechanics, it's just the same. You have a theorem. It's called the area theorem, which is telling you that the area of black hole of trapping horizons is something which increases with time. And finally, you have the third law, which is you cannot reach T equals 0 in thermodynamics. And in black hole mechanics, it's exactly the same, that you cannot reach extremal black hole solution. Extremal black holes are kappa equals 0, temperature equal to 0. Of course, it would be nice to give a full course on black hole thermodynamics. I just enunciated the law. But it's just to say that you have this correspondence. So this correspondence is actually it arises there, and it is defined. So the thermodynamical entropy of a black hole is proportional to the area. The law of black hole mechanics cannot really tell you the proportionality constant, but then once you fix the temperature with the definition that we've done there, you get that it's the correct proportionality constant. And again, this is not the only way. You have I was discussing with Ivano before that I was mentioning that if you do the computation of the Hawking radiation with the path integral, you do get exactly the same. That the thermodynamical entropy of the black hole is this quantity here. You also have some other arguments. One is the so-called Bekenstein bound. Yeah. Yes. The fact it has to increase and decrease is just that if you assume this, then there is a bound. So this red curve should always be below the black curve because this is the area. The black curve is the area, and so this is sorry, the red. I didn't write it down, but this is the let's say the entanglement entropy of a black hole. Right? Entanglement. So the red is this. So it must be below the area. It must be below this black line. But again, I want to stress that you are adding another assumption here. Right? And then, I mean, there are justification because if there were no justification, then, I mean, and then there were. Yes, the peer-to-peer assumption is, thank you very much, is because in order to have the peer-to-peer assumption, the Hawking radiation must be, as I said before, it has to be entangled with the microstates that are inside the black hole. Because I say that there is a flux of energy going inside, and there is correlation. But if I can limit the amount of information that can be inside the black hole, then there is the problem. If I do not limit, there is no problem because the black curve, this one, is just the Hawking, it's just the entanglement entropy of the radiation. And I want this to be equal to the entanglement entropy of the black hole because I want the total entanglement entropy to be 0. Right? Maybe I just assumed that you know that, but if you compute the entanglement entropy of a pure state, that is 0. We just call it S of a pure state that is equal to 0. If this state is a pure state, but you can divide it into two subsystems, A and B. This means the entanglement of A and B is 0. So if I take the entanglement entropy of the Hawking radiation and the black hole, the total one is 0. But if you trace out some degrees of freedom, this is what I assumed, that maybe that's why it was not clear. If you trace out some degrees of freedom, the entanglement of the system A is not necessarily 0. And the entanglement of the system B is not necessarily 0. But this is only true, but then you must have the entanglement of the system A is equal to the entanglement of the system B. Okay, so if you have two, so they don't need to be 0 separately. So Hawking radiation and black hole, they don't need to be 0 separately, but they need to be equal. And that's why these two curves must be same. So thank you for the question, because I think that maybe I should not have assumed that everyone knows this relation. Then there is a Bekenstein bound, which is basically a bound that is telling us that the amount of entropy, entanglement entropy that uh, can be included in a region of a given energy E and radius R is bounded. So is smaller or equal than a given quantity that now I don't remember. It will be in the notes. Let's say S naught, some quantity. But the point is that when you specify this for a Schwarzschild black hole, you get that the entanglement entropy is smaller or equal than the area over 4G. Right? So this is another reason why you can think of that. And there are also generalizations called Busso bound that give this result. Uh, and finally, there is holography. If you believe that your full theory of quantum gravity is holographic, then this is the entropy will be given by the area. You cannot have something extra. You cannot have volume terms or so on. Okay. So, any questions up to here? Yeah. No, I think they are model dependent, and I never managed to understand the computation. If I need to be completely honest, you mean about this uh, island conjecture? Yeah, I mean that's very nice because there you just you get a way to compute the entropy of radiation, which is inspired uh, mm, by system with that have an holographic description using the Ryota-Kayanagi formula. And then you just take this formula and apply to the semi-classical system, and you get something which depends from which follow the page curve. But it's something that you can compute in the semi-classical description, but it's something that is justified only by some some holographic description, and also it's something that I mean there are subtleties I never managed to fully understand in there, to be honest. So, for instance, when you do this computation, you need to consider also the interior of the black hole spacetime to do the computation. And I don't understand if this is just a mathematical trick or if it is something you actually need to construct the state. Because if it is something need to construct the state, I mean, this is just the standard, the initial picture of you need to check whatever is inside. But I don't know. I'm not able to understand because I asked to several people working on that and I got different answers. So no, I mean, no, but the justification of that formula is come from a system that does contain, yeah. No, but the presence, I think, of the saddle, I don't know, I'm not an expert, but I would say that there are some specific saddle points you assume to be that they require holography to be justified, I think. That is not those. Okay, maybe I don't know. I'm not really an expert on that. Yeah. Mhm. Yeah, of course, of course. Um, but now I want also to say something. I mean, I think that most people would agree on this formulation of the problem, but I need to say I'm not one of them because uh, I want you to know that this is when I mean it's not the standard interpretation. The reason why I'm not one of the people that believe in this impression, again, I said this is a problem, not a paradox, because we do have a consistent description within the elements that we put in. The description is consistent. We never put back reaction, and we never put this limit. And so the computation that we can do is just telling us that uh, we are getting more quanta than the area. So the entropy of the black hole is actually exceeding that limit. So within the model that we have, we are indeed violating this assumption, right? At some point, this model will violate this assumption. So now then there is the problem because we need to understand better how to include the back reaction and so on. But I will not say that there is a paradox in the way that we have uh, a we start from some uh, we start from a well-defined theory, we do some well-defined computation, and we get an inconsistency. I don't think this happens. I think that within the model that we do, there is no inconsistency. And then once we add this, we find that something which is indeed inconsistent. But then I want to mention something that this bound here. These justifications here that the entropy is actually proportional to the area. This is the thermodynamical entropy. And I did say that the von Neumann entropy is always smaller or equal than the thermodynamical entropy. But there is actually, I think, a caveat. And it is like when we compute the entropy of states, which is like we can divide into sub system. So the von Neumann entropy of system A and B. I've written there, and this is true. I mean, this you can check in 2 minutes. So let's just start from the definition of the two. Smaller or equal than the thermodynamical entropy of the two subsystems, right? Of the full system. But of course, if I consider this quantity here and the thermodynamical entropy of one part of the subsystem, I mean, this could be less, equal, greater, because we're not taking the full subsystem, right? The full system. What am I doing here? So why am I doing that? What I mean by that is that if you take the two system A and B close to each other, you define these quantities, you get this inequality here, right? But then if you take these two boxes, they are entangled because you do some interaction, etc. And then you take these two and you put them very, very far from each other. You can definitely study the thermodynamics of system A without worrying about the thermodynamics of system B. But you'll never be able to study the von Neumann entropy of system A without thinking of the von Neumann entropy of system B. Because the entanglement works even if the two subsystems are space-like separated. Right? So all that I want to say here, and again, this is just my opinion, and it's definitely not the accepted opinion by most people, just very, very minority of physicists that would agree with me. So I just want you to know that. But I want also to warn you about this possibility, is that whenever we do this computation, uh, we are only counting the number of degrees of freedom when we study the thermodynamics that are available for an observer outside, which are degrees of freedom that are on the horizon. Because everything which is inside the black hole is never going to be accessible for an outside observer. So whenever from outside I do some computation that I want to compute the thermodynamical entropy, I can ignore these degrees of freedom. They will not play any role. So all these, they will not be all this the computation. They will not be influenced by whatever is inside. But when I want to compute the von Neumann entropy, I cannot do that. So I just want to warn you that this is a possibility that that area, thermodynamical entropy, counts the degrees of freedom that are a thermodynamical system accessible for an outside observer. But the degrees of freedom that are incoming because of Hawking radiation, they will be completely lost from outside observer. So I cannot use them to describe the thermodynamics. And also the Becker-Stein bound does not really work when there is strong gravity effects. And this generalization, the Busso bound, does not work when you have a violation of energy condition that, as Ravan pointed out before, it's something that you do have with Hawking radiation. Right? But again, the main that I wanted to discuss in this was just the basics of the problem, was the formulations of the three problems, the three possible formulations of the problem, and the fact that I wanted to warn you that the fact that this assumption is usually not stated out loud. So you say the information loss paradox is a contradiction between one of the cornerstone of quantum mechanics, which is pure state into pure state, and something which is general relativity and evolution of the states and doing quantum filtering on curved spacetime. But you should know that there is also a third one, right? And you should know that that should be justified. And of course, there are theories of quantum gravity where this arise. So if you, for instance, if you like string theory, then of course you will have a very strong very strong motivation to accept that bound, and then the theory should provide some resolution. But that's why I don't call it paradox, because if I don't assume anything on the UV completion, there is no contradiction with the computation we can do. Okay. Yeah, this was just a very quick introduction. And then in the last 20 minutes, given several of you asked me to talk about a little bit about regular black holes, I will do that. But before, I want to stop for questions.
So let's say I have a quantum gravity theory.
Mhm.
I would expect there is no.
Yeah.
Is there still a problem?
What is still a problem?
Radiation, let's say.
Mhm.
Is
But
expect that there's an issue like that?
Yeah. Well, actually, this is actually a good starting point for talking about regular black holes, because what you do when you talk about regular black holes is you assume that there is no singularity. You try to give a little information as possible about the system that lead there. You make some assumptions, of course, and that could be something that we can discuss. But to have a short answer, yes. If there is no singularity, I would expect the information to pure state to go into pure state. No singularity or no event horizon. So, I mean, I'm completely fine with the fact that if I have a singularity and in the classical picture, whatever goes into the singularity goes destroyed and leaves the universe, then yeah, I mean, it's lost. But also, if I take a Cauchy surface, if this lies in the future, it's always there. Like whatever is creating the matter, at any time, it's always going to be on this. Like I always need to take into account to define the state. And I don't really understand what's happening at the horizon crossing, because you define the states always on a Cauchy hypersurface, which is always a space-like hypersurface. So the fact that this is outside the horizon and this is inside, I don't really know what's changed, because even here, these and these are space-like separated. Like it's not really the horizon; it's just the definition of the hypersurface, which forces you to have something which is space-like separated. But of course, this is just my opinion, and as I said, it's not the main opinion. Yeah. Well, something else I wanted to say here, I forgot. I wrote here T, and that's what everyone does. I have no idea what T means, because on Scrape Plus I count T, I count U here, but this is not a good coordinate on the horizon. So what you will do, you say, okay, I'm close to square plus, and I do a foliation, right? And so t is the time of the foliation. So t grows from one slice to the other. But then there are several ways I can do the slicing. And so there are several ways I can change the fixing the time here. There are several ways I can continue the slice. And so there are several ways. So I will change the area of the horizon at that given time because this will change, right? There's no eternal time. But the argument does not really change. It's just that the shape of these lines change, but the argument is kind of solid. Yeah. You need to choose a clock that is also good at your horizon, and but yeah, anyway, you do that, and then whatever is your foliation, it's consistent. Yeah, 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 exactly. But I mean, this is not a good time on Scray Plus, so technically speaking. But anyway, this is fine. You first choose the foliation and then that change. I just wanted to be precise because I wrote T, but yeah, what is T depends. Okay. Mhm. Yeah. Mhm. But again, is this formulation here? Is this formulation here? I completely agree. So this does not have anything to do with the singularity. It's to do with the horizons, the causal horizons. You can have causal horizon without singularity, but it's not worrisome for me because if something leaves the causal, like if something enters to the horizon and then I cannot access it, I'm completely fine with losing the information of that because it's something but I don't think. Uh, yeah, but outside of servers can go inside the black hole. So if you then want to check the state, yeah. Okay, 15 minutes or so, like a little bit more maybe. I just want to say a couple of words on regular black holes because uh, of course black holes are one very good reason why we're looking for a theory of quantum gravity, and the reason is not Hawking radiation or horizon stuff because we can have semi-classical gravity, kind of works well with the limitation I just described. The reason is singularity. It's the fact that within classical general relativity, we have some theorems. The first one due to Penrose in 1965, that this theorem is telling us that under reasonable initial conditions, you will go and form a singularity, which is a point where you break down the theory. Singularity is defined by geodesic incompleteness in this theorem. So you don't need curvature invariance to blow up, but you need some geodesics to be incomplete. And then you can prove that. So basically, the assumption of this theorem and subsequent theorems are that you formed a trap surface. Remember, trap surface, as I defined in the first lecture, are surfaces where you're locally trapped. Locally, you cannot move in the direction of increasing radius. Locally, you need to move in the direction of decreasing radius. Then the other assumption is that you can use the standard tools of differential geometry. So you consider manifold and matrix on this manifold. Then you assume something on the space-time, which is that the space-time is globally hyperbolic. There are some other theories that get rid of this assumption and substitute it with something different, like uh, mm, well, but anyway, for now we can use this one. And then you assume something on the either the dynamics of the space-time or some condition of what you expect gravity to do, which is the null convergent condition, which is basically telling you the gravity is always attractive. Now, within general relativity, so Einstein field equation, you can write this in terms of the stress energy tensor, and this is the null energy condition, which is telling you that the energy is positive. But like we are specifying the dynamics of the theory, this is just the gravity is always attractive. Yeah. No, this in general. In GR, the fact that uh, this is telling you that the energy is positive, and positive energy in GR is attractive, right? Because this is just the Ricci, this is just the curvature. Yeah. And then with this assumption, you prove geodesical incompleteness. Incomplete. Yeah. Yeah. This is Ricci tensor. No, no. Yeah. Incomplete. Eh. Okay. So this is some physics. This is something that we do not like because we don't want to lose predictability in the theory. We want to understand what are the geodesic doing. So what you need to do is to violate some of these assumptions. First one you can violate is avoid the formation of trapped surfaces. But this will imply that I mean, there are very reasonable initial conditions in general relativity that give you trapped surfaces. I was discussing before the possibility that semi-classical gravity avoids the evaporation of trapped surfaces, but I told you that semi-classical gravity alone is not enough. But of course, this is something you can have. For instance, you can replace black hole with ultra-compact horizon-less objects. I would say it's difficult to form them without forming a trap surfaces first, but this is something you can avoid. And then, of course, you can neglect this possibility here. So you can say, okay, no, space-time at high energy cannot be described in terms of pseudo-Riemann geometry and smooth manifold and a metric. And this is definitely a possibility. And I mean, several quantum theories of gravity do that. But even if this is true, sometimes it's possible to have some effective geometries that are describable with these tools. Right? And also these tools are tools that we can use very well. So this, as a working assumption, we can start by assuming that this holds. But again, this does not necessarily mean that the true theory of quantum gravity will always use these tools. It's just that you can describe an effective geometry. This is something that is just, once you assume this is just telling you something about the evolution of the theorem must be well defined. And this is something which is very easy to negate, right? Because you change the dynamics of gravity or you change the energy content and then you negate that. And so what we can start doing as the simplest possibility is to describe the possibility that still satisfy this with the caveat that maybe you can want to also assume the absence of trapping surfaces of ultra-compact objects. And you just violate this quantity here. Yeah. Yeah. No, I mean, what? Mm-hmm. What? No, I mean, there is the conjecture, cosmic conjecture censorship that tell you that you don't want negative singularities. There are several formulations of the conjecture. I don't want to enter into details, but let's say there are no negative singularities. But yeah, you can consider them. Mm. Yeah, you're talking about the two holes, of course. Yeah. But I mean, if your theory makes sense of this singularity, then you can even have them. But you need a theory that makes sense of them. Well,
While the discussion.
yeah. Yeah. Okay. Also because we have very little time. So so what you can do is to take space-time that violates this. You do form a trap surfaces, but you do not form any singularity just because you can violate the assumption of the theorem. And basically, what you need is you can see this means that the light gets focused. So gravity keeps focusing more and more the light rays. So you need somehow to defocus the light rays. And it turns out that there are not that many possibilities. If you assume that you can still describe them with some effective metric, there are not that many possibilities. Of course, in spherical symmetry, they seems very little because spherical symmetry, you have very restrictive symmetries. But also, if you go a little bit beyond that, there are not that many. And one possibility is, for instance, regular black holes, in which I will write something now. But the point of regular black holes is that you replace the central singularity with a regular core, and this core is surrounded by an inner horizon, and everything is perfectly fine from the point of view singularities. So the Peros grammar will look something like this. If you look at the Peros diagram of the collapse, again, I don't know how many times I have drawn this. What you do when you consider the collapse, gravitational collapse, at some point you form an horizon, a dynamical horizon, not an event horizon. And then this horizon is split into parts. One is the outer horizon, which in Schwarzschild becomes the event horizon and r equal to m and goes up to infinity. And the other one is the inner horizon, that in GR goes to r equals 0, and you form the singularity. And this is the Oppenheimer collapse we discussed also several times, that you do have the event, like the event horizon and the trapping horizon do not coincide. So what you want to do is not to allow the horizon to go uh, up to r equals 0, because otherwise you will form the singularity. And so these are the marginally this is the marginally trapped region, where inside you are in a trapped region. Observer inside must move in a direction of decreasing radius, right? They feel trapped. But the one possibility is that this actually only lasts for a finite amount of time. And so the matter does something like this, and then it goes back into some region which is perfectly fine, which is not trapped. And then we can draw let me do a little bit smaller. Okay, so you have a trapped region. So in here, you can always go, you must go in direction of decreasing radius, but you don't form any horizon, any singularity. At some point, you have something non-trivial going on. And here, for instance, there should never be a pure state going into a mixed state, because whatever enters, at some point it will go out. Right? So you feel like you're going over smaller and smaller radii, but then at some point you can go out and go to a asymptotic future. And now, why did they say it's a problem, not a paradox? Because if you assume this, then whatever enters must go out, but we have no idea how. And there is something non-trivial now to understand how that will go out, right? But this is uh, something that must happen. And as I just mentioned before, I say that smaller and smaller radius, just to give you an intuition of what that will look like. So if you look at constant radius surfaces here, they do something like this. So you can the radius in this line is smaller than the radius of this one. You can go from here to here with in a causal way, and you can also go from here to here in a causal way, larger to smaller. Right? But then once you arrive here, what you must have, let me try to do a decent draw. You must have the constant radius hypersurface must be space-like. So if you are inside, you can never move at a constant radius because they must be space-like, and then constant radius hypersurface become time-like again. Yeah, something like this. So if you are here, you will see the area radius to decrease and decrease. No matter how much you try to run away, this will decrease and decrease, which is what happened in a eternal black hole inside the event horizon. But then at some point, the fact that the geometry is dynamical, you will actually escape. And of course, then, I mean, I'm not telling you anything about what is happening here, what is the dynamical processes. This can be an extremely long time. Imagine this is related somehow to Hawking radiation. This is something which is extremely long. Or this can be something very fast, like you have something which is collapse, and then you just bounce. And when this happens, actually, there are models in which what you do is you switch off gravity at short distances. So you have something which is collapsing, and then it bounces, and then you have this explosion. And what usually happens is that this trapped region is often accompanied by an anti-trapped region, which is a region which is very similar to white hole. And this is something which, on the other hand, it's the opposite. You must go in direction of increasing radius. You cannot stay stationary, constant radius, but it's because it must always increase. So it's something like this. These are the constant radius hypersurface. Right, so if you're here, the smaller one, the radius must decrease because you need to go from here to here, and this is a smaller radius than this one. But in this one, you must go into direction of increasing radius. So this space-time describes something which is, you have something which looks very much like a black hole for some time. It can be very long, can be very short. And then you transition to something which looks very much like a white hole. Again, for a time, it can be very long, very short. And this is one possibility. Another possibility is that you can change the topology of space-time, and there's something which looks like a wormhole inside the trapped surface. I will not draw a diagram here at the moment. And then what do you do once you have introduced these spacetimes? Like you have no field equation to describe this or this completely generic, but you can write down some geometry, like some line elements, which are usually just modification of partial geometry with some extra parameter. And then you can do stuff with these geometries. You can study some consistencies. So you can study whether or not you can spotlight potential problems. For instance, as I mentioned before, in order not to have the singularity, I just said very quickly, in order not to have the singularity, you must have this inner horizon. And in general relativity, you know the inner horizon are stable. And there is something you can say also here without using the field equation, which is very cool because the fact you don't need the field equation, of course, the result is less strong. But then you can say that there are some issues even without knowing the field equations. And this is something very interesting that you can do that just purely by geometrically. And then you can do that. Then you can look what are the other implications. For instance, you check the internal consistencies. You can check what are the possible phenomenological consequences, and so on. You study the properties of these geometries. And knowing that there are several models inspired by quantum gravity, different approaches to quantum gravity that do lead to something that looks like this, right? But okay, this was just a few words. And of course, there will be a lot to say more. Then, I mean, you can start constructing different models. You can play, as I said, with the topologies. You can play with the bounces. You can look how the quantum stress energy tensor we described before looks on these spacetimes. The quantum stress energy tensor was mostly kinematics, right? What we discussed. So you can do something similar also here. You don't need the field equation. So there are several questions you can ask without the field equations. And then you can work out the phenomenology and the implications, and we can discuss about whatever you want about this. This was just something like 10 minutes.
So here the those type of is very powerful because it like complicate the method of the
Yeah.
dynamics. You just make a geometrical
Yeah.
arguments.
Yes.
What if in our complete theory of quantum gravity metric is replaced by something else? So with such a
Yeah.
So,
Of course. So when I say this is powerful, it's also accompanied by some weaknesses, because the most, I mean, like the most generic your argument is, the least stringent it must be. So you need always to look for something in between. And of course, as I said, this assumption here could be violated, and then you might you will throw away everything here that you have described here. But the point is, well, first of all, this is a working assumption. And then you look at the consequences, and then either you like the consequences or you change the starting working assumptions. And also that, I mean, if this happens, that you replace the matrix all in some compact region or I don't know, then maybe this description still does make sense. You can still draw some hints from here. In fact, I mean, he's working on the quantum loop models, and yeah. And then you have this type of diagrams, but you have some regions in which this description breaks down. And so, from the point of view of this approach, this is effective geometry, magic, effective geometry. From the point of view of quantum gravity, this is quantum gravity. Like the magic is replaced by quantum gravity. So, yeah. So even if this breaks down, even if this breaks down somewhere, you can still learn something. Very long question. Okay, it's a little beyond the lecture and related about the negative energy on the Peros diagram, which mentioned during the lecture. If enough negative energy can justify wormhole thought, or we assume we can deny singularity by existence of any wormhole type. I am curious to see what happened to Peros diagram in this step. Yes, I mean, of course, within this model, we didn't study back reaction or anything. We did model of working evaporation. And here I only mention things that do not change the topology. Of course, you can have some geometries in which you do change this. Let me dt squared plus f over dr squared plus r squared over d omega squared, right? So if this function r, capital R or small r, is something which has a minimum, you do have a wormhole structure. And if you place this minimum within the trap region, that's exactly what you asked would happen, that you have something which will form an inner horizon, a trapping horizon. Then you will have a wormhole inside of it, which could be a traversable wormhole or a non-traversable wormhole, depending if the throat is space-like, is time-like. So there are you can play a lot with this type of geometries. I mean, there are a lot of works by there is this geometry called people call it the Simpson-Visser geometry, which is studied a lot recently, and also the rotating counterpart. So yeah, there is a lot you can play on with, but whether or not this can be created because of the negative energy of the Hawking radiation is actually very interesting, but it's not within the model, but it's actually quite interesting to think about. So yeah, thank you for the question.
Thanks, Francesco.